Welcome back to the NET Physics series. Today we'll start the topic of oscillations, which is the seventh chapter of this series. Now, oscillations is simply a back and forth motion, or it can be an up and down motion. So, if something moves in one direction and opposite to that direction, so that's called oscillation. Now, I can give you an example. Consider you have a spring which is attached to a mass. Now, suppose at this point the mass is resting, so it's not moving. But what if I pull on this mass in this direction and then release it? So when I pull the mass to this direction, it will come from here to here and then it will start oscillating. So what I mean by that is, if you can think of this scenario in your head, imagine it. What happens is it moves in this direction and then it will come back to this direction and then it will keep oscillating until it dies down due to friction. Now let's talk about something that's called simple harmonic motion. Now the example that I gave you over here is of a simple harmonic oscillator, or just you can say a harmonic oscillator. So it's an harmonic oscillator and you can abbreviate it with SHM. So what is a simple harmonic oscillator or simple harmonic motion? Suppose I were to displace this mass in this direction by applying some force, right? So what happens is that this would be a vibratory motion, right? And now when I pull it in this direction, there will be a force that acts on this mass which would want to take it back to its original mean position, we call it. Now, mean position is this position where this block is resting at the moment. So this force, which is going to pull the block backwards towards its mean position, it's called restoring force. So we represent it with this F, and so just to differentiate, I'll just get rid of this F. Now this force is proportional to the displacement that I moved it in this direction. So let's say I moved it some x displacement. So you would expect the block to go in this direction, right, towards the mean position. So it's basically proportional to x, but in what direction? It's proportional to x in this direction, which means that I should have a negative sign to include for this direction, which is, rather than the positive side, if this is positive, then this has to be negative. And that's why it's proportional to negative x. And now the constant of proportionality is called k, which depends entirely on this spring. The shape of the spring, the geometry of the spring, and the material of the spring. So hence we have this expression which is F is equal to minus kx, and this force is called restoring force. Now, a simple harmonic motion is described as a vibratory motion in which this restoring force is directly proportional to the displacement from this mean position, and it's always towards the mean position. So if my displacement is in this direction, then the block will move towards the mean position, so it is moving in this direction, which is negative, and that's why we have this negative sign over here. Now in theory, at least, you can say that everything can be approximated as a harmonic oscillator. So for example, you have a pendulum a pendulum is going to oscillate like this, and then it's going to come back like this, right? And so the mean position for this pendulum would be this one, right? And these are the two extreme positions, right? So another example could be molecules or atoms, right? So if you have a chain of atoms, consider you have a substance and it's made up of layers of atoms, right? Now every atom is moving, so basically no atom is stationary, right? So the atom is going to oscillate in these directions about its mean position. Now from this we can also conclude that a simple harmonic motion is the one in which the acceleration is proportional to the negative of the displacement, right? Because F is what? F is ma, right? And so this is equal to minus kx. Now if I ignore the constants, then acceleration is proportional to minus kx. Such type of motion is called a simple harmonic motion, and it's actually one of the special types of vibratory motions. Now this acceleration, always note that it's directed towards the mean position, and that's the reason for this negative sign. Now if I consider this case of a simple pendulum, for example, I can define something that's called periodic motion. Now in periodic motion, what happens is that it's a type of motion which is going to repeat itself after equal time intervals. So what I can say about this example is, suppose that this is the mean position. Now I displace it like this, and then I release it from this point. So what is going to happen is it's going to oscillate like this. So what's happening? Once it goes here and comes back to its original position, to this extreme position, it has completed one oscillation. Now that means, and now if it does that again and again and again and again, then that's called periodicity or periodic motion. You can also define what is called the time period. And time period is basically the time that it takes to perform one complete oscillation. So it's resting over here, I pull it to this point at this position, and then I release it. So what happens is it's going to go to this point, and then it's coming back to this point. Now once it has come back to this extreme point from where I released it, one oscillation is complete. And so the time that it takes to come back to this extreme point is known as the time period. So time period then is defined as the time that it takes for a body to complete one oscillation is defined as then the time period. You can also define something that's called the amplitude. So basically, if I again consider this example and I take this pendulum and I take it to this position, now I release it, it's going to start oscillating. Now the maximum distance that it can come from its mean position to its extreme position, the maximum distance that it will rise is known as the amplitude of this oscillation, right? So then one can define the amplitude as the maximum distance that my body is going to move from its mean position, right? So in this pendulum case, the maximum distance that this pendulum rises, you can say it's not really the distance that it rises, but it's this distance that it's going to move. And that's the amplitude of this oscillation. Now you can see that this thing, it's kind of an rotational motion, and we can define the angular speed or the angular velocity with which it's going to move, right? So the pendulum with which the pendulum is going to perform its oscillations, we can define angular velocities for those oscillations. So the angular velocity is defined as omega equals 2 pi by t, where this t is the time period and 2 pi is 1 revolution. So 1 revolution is equal to 2 pi in radians. So 1 over t is actually your frequency of the oscillation. So you can also write down the angular velocity in terms of the frequency as 2 pi times f, which is the frequency of the oscillation. Now coming back to this pendulum problem, you can see that when I move this bob away from its mean position like this, it actually displaces with an angle theta, right? So I can define an angle theta, which is basically the angle that this bob is going to move away from its mean position. So we call this angle the phase angle, and we can define this phase angle as something which specifies the direction and the displacement of your motion of that particular point. In this case, it's the bob which is executing this simple harmonic motion. And you can define your phase angle theta as the product of the angular velocity times the time it takes to cover that displacement theta. Now suppose at time t equals 0, which means at the starting time the bob was initially at its resting position. In that case, the angle theta would be equal to 0. But you could also have a case where instead of all of this, your resting position was actually this one, right? So if let me use a different color for that actually. So let's say that this was my resting position, and then I release it and then it comes back to this position. So for example, if that's the resting position, then you can basically define something which is called a phase constant as well. Now this phase constant gives you the information about the initial value of this angle theta, and that's the phase constant. So at t equals 0, whatever value that I have for this angle theta is the phase constant. So it at t equals 0, whatever angle that I have, which is theta, is going to be given a new symbol, which is this psi, and psi is the phase constant, right? And it's the angle at time t equals 0. So this is my phase constant. Now suppose that if this phase constant psi is minus pi by 2, sorry, I used degrees, it's radians. So if it's minus pi by 2 radians, which is actually minus 90 degrees, then I can define displacement function, which is x, right, which is a function of t, as x naught, which is the you can say it's the amplitude of the oscillation, times sine omega t. Now because you have this phase constant with it, so at time t equals 0, it was not, the angle displacement was not 0, but it was minus pi by 2 radians. So I can write this, I can include for this in my expression as plus pi by 2. Now we know that sine, if there is the plus pi by 2 in the argument of sine, then this thing becomes x naught cos omega t. Now, the reason I used cos or sine, for example, you can say I use sine in this expression, was because it's an oscillatory motion, and we know sine and cos functions are those functions which are oscillatory, right? So, for example, this is a sine function. Similarly, a cos function is just if I change, so here we have theta, right? And here we have the function, which is a function of theta. So you can say that if I changed my phase to this point, which is, this is pi by 2, and if I shift my this vertical axis in place of there, if I take this axis and I move it at this point, so I'm causing a phase change of what? Pi by 2. So that's the reason that we do this plus pi by 2 for the phase change, and you can see from visually that this function basically became a cos function, right? So it's starting from pi by 2 where its maximum value is this one, which is x naught in our case, right? So that's the theory behind this thing, pictorial theory. Now let's move our attention to what is called the horizontal mass spring system. It's the similar system that I drew before for you, and it's where you have a spring that is horizontally attached to some mass m and performs an oscillation. Now, for this spring, I can define something that's called the Hooke's law. It's actually named after Robert Hooke, and the law basically states that the strain produced in the spring due to the force that would be applied to pull this mass in this direction is directly proportional to that stress that was applied to this mass, right? Or to this spring, you can say, because when you pull this mass in this direction, you're applying stress on the spring. Now, this thing remains true until something that is called the elastic limit. Now, elastic limit is basically that limit where if you consider a spring like this, right? So let me just draw a spring, right? So this is your spring. Now, if I attach something to this spring, it's going to, because of the weight of gravity, right? The weight of this object, what's going to happen is it's going to keep pulling it downwards, right? So maybe if the mass of this block was not high, so the spring, if without the mass, if the spring looked like this, then maybe when you remove this mass, it will still keep looking like this. But what happens if the mass is too heavy? So for example, you attach some big mass to it. Now, in that case, what might happen, what could happen, is that when you release this mass, when you remove this mass, the spring might look like this. So it's not coming back to its original position. So basically, at this point, the elastic limit has been crossed, and so strain was not directly proportional to stress in this case, and hence the spring could not go back to its original position. Graphically, you can represent this situation as you have stress, which is usually denoted with sigma, right? So I'll just write it, and strain, which is denoted with epsilon. So stress over strain graph you have here, right? And now the relationship between the two looks a bit like this, but now what happens is that this is linear, right? So this is fine. This strain is directly proportional to stress. You can see that. Elastic limit is that point where this thing is no longer true. So what happens is you can say that it kind of curves like this. So the elastic limit has been reached at this point of strain, right? So whatever value is here and whatever stress was applied. So you can check for which you can, by looking at these graphs, you can see at which applied stress will I break this elastic limit, right? Now you can find the gradient of this graph, which basically is stress over strain, and it is defined as the Young's modulus with E. So it's Young's modulus. Now this Young's modulus gives you information about a lot of things. It gives you information about the nature of the spring and well, a lot of things, right? So that's your Young's modulus. So now for this system, I can write down an expression for acceleration using Newton's law, which is F equals ma, but this F for a spring is the restoring force, which is minus kx, and hence this gives me an acceleration of minus kx over mass of the body. So that's the acceleration, right? And this is the acceleration for this mass which is attached to this spring, and it's performing a simple harmonic oscillation. Now you can also write down the angular velocity for this thing, which is omega is equal to square root k over m, where k is again the spring's constant and m is the mass of this object which is performing the oscillations. Now the interesting part over here is this is actually a differential equation, and it looks, if I want to work in terms of x, right, which is the displacement, then the double time derivative of x is acceleration, right? And so I can always write down these double derivatives as, so any time derivative, so for example if I have d over dt of any quantity, then that can be written as a dot on that quantity. If the derivatives becomes 2 times, so there are two time derivatives of that quantity, you can write it as x, now because here the quantity is x, and you can put 2 dots on it. So this is just telling you it's the double time derivative of x. So now if I replace this in this expression, it becomes mx double dot is equal to minus kx. You can rearrange this entire expression as x double dot minus kx over m. Right, so there will be an equal to sign over here. Now the solution to this equation, is x of t, which is a function of time. Now it's equal to some constant x naught, where this would be the amplitude of the oscillation times sine of omega times t, remember. But now what is omega? Omega was 2 pi by the time period and times omega times t. So this is the solution to this differential equation. And now if I were to say that I want to solve a system of this simple harmonic oscillation, this x of t is the solution to that system, and now I can put any values of t and I can find the displacement at any given time t of my oscillation. Now let's quickly talk about springs in series. So for example, consider that I have a system which is like this, and you have several springs attached, something like this, to a mass. Suppose that this is mass m. Suppose this is one spring 1, this is spring 2, and this is spring 3. Every spring, if it's different spring, it would have a constant k to it assigned. This is the spring constant, which depends again on the nature of the spring, material of the spring, shape of the spring, and so on. So let's suppose that the spring 1 has constant k1 and spring 2 has constant k2, while spring 3 has constant k3. Now the combined effect of all of these springs together would be not a direct sum of these k's. So in series, the spring constants are added as follows. 1 over k is equal to 1 over k1 plus 1 over k2 plus 1 over k3 plus so on, right? How many springs you have. Now, this is an inverse addition of the springs constants. And then you can take the LCM of this result, and that would be your K, right? So it would be the I did not mean LCM, I meant you can take the inverse, right? So taking the inverse of this sum would give you K. So it's the inverse of 1 over k1 plus 1 over k2 plus so on. You can also write this in a shorter hand notation as k is equal to the inverse of sum I 1 over ki, right? So this just means the same thing as this, where this just uh, is taking the sum of all 1 over k1, 1 over k2, and then taking the inverse of the result. So that's how you basically add spring in series when they're attached in this series. So series is basically, so this 1, 2, so it's basically in a series, right? Similarly, you can also have a case where your springs are attached parallelly. So springs in parallel, suppose that you have a system that's, well, let me try to draw it. So you can suppose that you have something like of this sort. So again, there will be some spring constant associated to this spring K1 and some spring constant associated to this spring K2. Now, the resultant of K1 and K2, which would be acting on this block, is simple sum of K1 and K2. Now, if you think about what we are doing so far, it's kind of analogous to what you do in electronics, but in electronics, what you do is you add directly for series, but you add indirectly for parallel. So it's just the reverse of what you do in electronics in this spring system. So in parallel, you're just directly adding K1 to K2, right? Now suppose that you have a single mass attached to a spring. So let's just draw this thing over here. So let's write down some of the things that quantities we can have for this system. Well, first of all, let's write down time period of this system. It would be t equals 2 by m over k. Now, if you look at this expression, you can see directly that the time period is directly proportional to the square root of the mass that is attached to this system, right? So, which means that if the mass increases, then, well, time period would also increase. So the time for one oscillation would increase, but it would not increase with you can say linear or with power 1, but as a square root of m. So it would increase slightly slowly, right? So you can attach heavier mass, but it would increase as a square root of that mass. And this relation also shows that the time period is inversely proportional to the square root of k. So if the spring constant is higher for the spring, so you can say that the spring is more stronger, or it has a more reliable geometry or anything, where the k is high, then the time period for one oscillation decreases. So the oscillations are relatively faster in that case, where the spring constant is a better one. right? So if you have a higher spring constant, then the oscillations would happen more quickly. Now, remember that we defined the displacement as x equals x naught sine omega t. From this expression, it is very simple to derive the instantaneous velocity as simply taking the time derivative of this expression. Now, once you do that, you get square root k over m x naught square minus x squared. You can rearrange this expression as, if I factor out square root k over m, right, and I can also factor out x naught, then what you get is square root 1 minus x squared over x naught squared. Now, this thing over here is just the maximum velocity, right? Because this is the velocity at the mean position, right? So I can define this as maximum velocity with which it's going to come back to its mean position. And why is it the maximum velocity, by the way? So suppose again that you have this bob and it's oscillating. So you moved it here, and then when it's coming back to its mean position, at this point, all of the potential energy that it gained by increasing some height has been converted when it comes back to its original position into its kinetic energy, all of it. So at this point, the maximum thing would be the kinetic energy, right? And hence, kinetic energy is simply half mv squared. So the mass of the bob did not change during this course of motion. So the only thing that could have changed is velocity. So which means the velocity was maximum at this point, right? So hence, this is the maximum velocity, which is at the mean position, which is this thing. Now, what you can do is you can define the instantaneous velocity simply as the maximum velocity times the square root of 1 minus x squared over x naught squared. Right. So let's quickly discuss the case of vertical motion. Now, vertical motion, you could have something where you have this is a spring motion, right? So we are talking about spring motion. So you could have a spring which is vertically attached to a mass m. There would be a force of gravity downwards, which is mg, which is the weight. And so in this case, the restoring force will be in this direction, which is minus kx. So if I use the law of force, then I can write this equation as F, which is equal to mass times the acceleration due to gravity, because that's the force that's acting on this mass. And this would be equal to kx, right? So from this, then I can now simply x is the elongation of this spring. So that's why I did not put the minus sign over here, right? So x is how much of the spring elongated, right? So how much of the length increased of the spring due to this mass mg. So you have this expression, and from this expression you can write down x is equal to m over k times g. And so the time period for this thing is t is equal to 2 pi square root of x over g. So this x is just this x. right? And so that's the time period, and that's the um, displacement. Now, before this part 1 ends, I'll just like you to know that in one complete vibration, which I've been referring to as oscillation. So if you have a one complete vibration, the body is going to cover a distance equal to 4 times the amplitude that it could cover. So suppose that this is your, again, bob, and here it's moving like this. Now, in one oscillation, what happens is it's released from here, so it goes to this point. So how much of the amplitude it's covering? Remember, amplitude was defined as the distance from its mean position to its highest position. So that's the amplitude. So when it comes back to this point, so here also it would be a, the amplitude. So the total amplitude from going from here to here is 2a, which is half of oscillation. To complete the oscillation, it should also come back to its original position. So it would be 2a again, because you see a plus a. Now if you add these two, then you get 4a, which supports the statement that in one complete vibration, a body is going to cover a distance which is equal to 4 times the amplitude.